All right. Hello, everyone. This is an audio, a video that I'm recording to write some programs on loops and loop constructs. So let's just start with something very simple. So let's say we want to toggle port D bit 0 10 times. Then the first thing that I've done here is I've shown that the direction of port D is all output. Now what I need to do is to toggle it every time, and in order to toggle I can use one of the instructions that change bit 1, and I could use things like XOR and so on, but I don't need to use these fancy instructions. I can use increment and just increment port D, and assuming that only bit 0 is connected to an LED, then I should be fine. I don't care what the rest of the bits are doing. So increment F port D would do the job. And of course, so that would be the loop body. I can do just inc F port D, but I need to do this 10 times. And we talked in class today about the various ways of doing it. One would be to initialize a variable to 10 and then decrement it and checking to see if it has hit 0 and quitting if it has. So what I can do is I can just initialize, and let's say I have to choose the variable that I want, the loop variable. Let's say it's prod L, for example. So I'll do move LW, and then I said I want 10 times, so 0x0a, and move WF to prod L. So prod L is my loop counter, and this would be the loop that I will come back to. Has to be after I've initialized my loop counter, and then I would need so increment F is basically toggle RD0, again assuming that I'm ignoring the rest of the bits. And here I can do decrement F, my loop variable, and if it hasn't reached 0, branch not 0, go back up to loop. Otherwise, don't branch, which brings me down to this loop back, branch loop back, which is the end of the program. Right? Now, in the interest of time, I'm not going to simulate this, but I strongly recommend that you guys do and see that this indeed is going to iterate 10 times, and also look at look at port D, and you're going to see that it's going to increment from an arbitrary initial value that it has. I didn't even bother to clear F it, and then you're going to see that the least significant bit is going to change because you're counting up, and that would result in the least significant bit increasing. Now, let's say that you want to do something a little bit different. Let's say you want to toggle RD0, but you want to do it at an interval. And I'm going to pick an interval, and let's say I want to pick an interval which is, let's say, 1 microsecond. Now, in order to do that, let's first realize what the clock cycle is. So I said that the clock cycle that you use is 12 megahertz, right? So if I have 12 megahertz, then it means that one clock cycle is going to be 1 over 12 million seconds, right? And if I want 1 microsecond is going to be 1 over 1 millionth of a second, right? So in order to achieve a 1 microsecond delay, I need 12 instructions, because then I have 12 divided by 12 million. That would give me 1 million, right? 1 over 1 million, right? So if I want 12 instructions, let's see how many I have here. Here, this is going to take 1 cycle. This is going to take another cycle. This is going to take 2 cycles. So 4 cycles overall. And what I need to do here is to add instructions here that brings up the total to 12. Now I can do a bunch of move FFs. So if I do, I'm short of 8 instructions, right? 8 cycles. I can do 4 move FFs, or I can just add 8 no operations. So let's do 2 no ops and then 2 harmless move FFs. Let's move FF wreg to itself and do this 3 times. Okay. Now, if you look at the loop now, you can count the number of instructions that appear between loop iterations. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So I have 12 instructions. So every time that you hit that incf port D, there are going to be exactly 12 instructions in between. And if you're running off of an instruction clock cycle of 12 megahertz, then it's going to be exactly 1 microsecond. Now, another question would be, well, what if I want to generate a delay which is much longer than that? What if I want to do 1 second, or 1/10 of a second, or 1/100th of a second? Now, the number of instructions that you need to have in between is going to be much more, right? You need 100 instructions or 1,000 instructions in between, 12,000 instructions and so on, to provide that kind of delay. And obviously, you don't want to have many move FF instructions in between. So what you can do is you can generate other loops inside this loop, right? So I could potentially initialize. So let's say this is my delay X, and I'll do the numbers later. But what I can do is I can say move LW, and let's say I put decimal 100, and then move WF into prod H, a different loop counter. So let's just call it inner loop counter. And then I could have a bunch of no ops. The exact number of it I can work out later. But let's say I put 3 no operations, and then I can say decrement F my prod H and branch not 0. I don't want to go back to loop, right? I don't want to go all the way up to here. I want to go up to here, right? So let's just call this delay loop. So I can just say branch not 0 to delay loop. Okay. Now, how do I analyze this? Well, if I'm doing 100 times of the instructions that I have here, then you basically count the number of instructions inside the delay loop, and that's going to be 3 no ops, 1 decrement F, which is 4 instructions, and I have branch not 0, an additional 2. So I have 6 instructions, and I'm repeating this 100 times. So I get 600 instructions in between here, and just consider, well, and of course these will count as 2 additional ones. So the whole thing here is going to be 602 instructions, right? So it's equivalent to writing 602 no ops inside this loop thing, right? And essentially you can count that as virtually 602 no operations, and that would tell you what the delay is going to be for toggling port D. Right? Now, this is a simple example. I'm not going to finish the math here. I mean, you would need to, if I ask you to generate a delay of 1 millisecond between port D toggles, you do the math, and essentially what you do is you play with these numbers, and you would add more, or maybe remove some of these no operations, or change this number. Just be careful about the limitations that you have. So the maximum number that you can go here is going to be 255. Well, 256 if you start from 0. So you can't go beyond that. If you want more than that, then you have to do more fancy stuff. Either create a third loop inside this delay loop, or maybe use 2 variables as 16-bit numbers and do a 16-bit decrement. These are the things that I'll talk in class tomorrow, how to do 16-bit bit decrements and increments, or do add numbers that are 16 bits or 24 bits, etc. But this is one way. This is one way of doing it. So maybe just use a 16-bit loop counter and do 16-bit decrement and branch. Or an alternative would be to create yet another loop inside this delay loop that would give you maybe 100 instructions or 200 instructions, and you multiply that to whatever loop count you have here, and that would allow you to do thousands of instructions. And this is what you're basically doing in your lab 1. And if you look at the code looks scary, but there is nothing to it. I mean, it's essentially bunch of loops inside each other. And one of the challenges that is going to become frustrating when you try to put together a bunch of instructions to create a certain delay is that numbers might not be divisible to the exact values that you want. So you want exactly 600 instructions, but you end up with 602 instructions because you need to initialize variables too. And if you start playing with this number, maybe, well, decrease it to 99 and add a bunch of no ops after this line to make exactly 600 instructions. Again, there are more details that I'm not telling you, but you may not be able to make that. One detail that I did not factor in my calculations today is that B and Z, and if you consult the table, is going to tell you that it's going to be 2 clock cycles if the branch is taken, if the not zero condition is true, and it's going to take only 1 cycle if it is taken. So this is not going to be 600 instructions, the loop, it's going to be 599. And again, you would have to add and remove no operation instructions. And sometimes you will not be able to make an exact delay, period, no matter how much you play with these the number of iterations and the number of instructions that you have. And that's why later in class, in maybe 2 weeks or so, we're going to look at the timer modules inside the PIC microcontroller, which allow you to use hardware units that deliver exactly the delay that you want to work with. Okay, I'll keep it short so that you guys do watch these videos, but give me some feedback, if you found this useful and if you want me to continue recording stuff outside class. Thank you.